Okay, last week we talked about fatigue, and the only case that we considered was the completely reversed case of fatigue. And generally, our loads are very seldom completely reversed. So therefore, we need to come up with ways to analyze situations in which the load varies from some value to some other value with no rhyme or reason, basically. They could both be positive, both negative, one positive and one negative, or anywhere in between. Which of these 6 diagrams depict what we studied, the completely reversed load? Somebody said something? F. This one. Remember, in the completely reversed load, the load varies from a maximum to a minimum, and the magnitude of the maximum value of the stress and the minimum value of the stress, the magnitude, are the same. So, for example, it goes from -2 KSI to +2 KSI. The magnitudes are the same. One is tension, the other one is compression. You can have loads like this, with that variation, where the maximum is tensile, the minimum is compressive, but there's no, the two are not the same, so this is not a completely reversed. Or, in this case, the magnitude of the maximum tensile stress and the maximum compressive stress are not the same. The tensile is more than the compressive. Could have it this way: tensile less than the compressive. Or something maybe with a double hump like this. That's much more difficult to analyze. Or something like that. Both values positive, and you never reach 0. So the minimum is some positive value of the stress. The maximum is another positive value of the stress with a higher magnitude. And a very, very common situation, a situation in which a load varies from 0 to a maximum. This, for example, would be the case if you neglect the weight of the structure in what bridges see. Bridges see trucks and cars coming over them, applying a force, going out, no force. And if you neglect the actual weight, then that would be the case. In order to analyze these different types of loading, all of which are called fluctuating, rather than completely reversed. We define a number of variables that we use often. So let me draw something here similar to what you have on the board. Stress versus time. Something like that. This is the maximum stress. That's the minimum stress. And we define mean stress as the sum of the maximum and the minimum divided by 2. Basically, it is what it says. Mean value of the stress. This case would be something like this. Sigma m. We also define alternating stress. Sigma A equals sigma max minus sigma min over 2. In this case, it would be either this value or that value, mean and alternating value of the stress. Therefore, we can write sigma max is equal to sigma m plus sigma a. There are some other stresses that are defined both on the graphs that you see. I'll magnify this graph here a little bit. So for example, in this one, there's your mean stress, where the dashed line is. Alternating. We also define stress range, sigma r. Just sigma max minus sigma min, what the name implies, the range of values of the stress. There is also another stress which is not shown here. We don't see this too often, but there are instances in which we see it, which is called the static stress. Mean stress, by the way, your book also calls it steady. I like the word mean much better. Static stress is a stress that is applied to the material and essentially has nothing to do with the fatigue loading. The best example of this is weight. For example, if you have a beam simply supported with a load that varies between some value some value up, some value down, we usually neglect the weight of the beam. And so we only look at the variation of that stress. But if we don't neglect the beam, then the stress neglect the weight of the beam, then the stress that is generated by that weight will always be there, whether or not you have fatigue loading. That's called static load. The two that we use 90% of the time or more are those two: the mean stress and the alternating stress. And so we would like to take a look and see how we would analyze a situation with this kind of loading. The fluctuating load. Make that a little bit bigger. I'm going to show you how that graph is drawn by drawing it again here. And for that, I'll just erase this. Let's say we take a set of axes like this. On the horizontal axis, we plot sigma m. On the vertical axis, we plot all other stresses. Sigma max, sigma min, the mean stress, alternating stress, whatever you like. So here, I should just call it, just like that graph, call it stress because it's a lot of them. This, however, the mean stress. Mid-range sometimes called as well. If I were to plot a completely reversed load in terms of, I remember that the completely reversed was that. If I want to plot, for the time being, sigma m on the abscissa and sigma a on the ordinate, what would be my sigma m, the mean stress? Zero, right? So I'd be here. And if I want this part that is under this stress, completely reversed, to have infinite life, what would be the maximum value of the completely reversed stress that I can put on it and still expect infinite life? We talked about this last time. Ring a bell? The maximum value is SE or SE prime, depending on whether you want to draw it for a part that you have, a real part, or for the rotating beam specimen, SE or SE prime. In this case, we'll just take SE, the corrected values. So, let's say this is the value of SE here. And I should draw it both as positive and as negative, correct? Because this is completely reversed. Goes from SE in tension to SE in compression. If my stresses are smaller than this, in other words, they plot over here, here, before I get to these, I can expect infinite life. In other words, if my stresses are over here, below SE, there's infinite life. Stresses above, there's finite life. For the time being, I just want to look at infinite life. So if we run tests and we find failures, then that means that the test stresses must have been somewhere there. Agreed? If we run a test and we do not see infinite life, then that means that the stress must have been larger than the endurance limit. Does that everybody understand that? Yes or no, please? Yes, thank you. So, I can call this region the infinite life region, or safe for infinite life, that region finite life. because there is no infinite life if the stress is larger than SE. Now, this is the case if the mean stress is 0. If the mean stress is not 0, for example, that. Non-zero mean stress. Tension in this case. We'll take a look at compression too. In order to preserve this infinite life, at least 10 to the 6 cycles, what do you think will happen to the alternating value of the stress? In other words, can it be still equal to SE? Let me go a little bit further. What if I increase the mean stress until it is equal in magnitude to this, but it's the mean stress? Then how much alternating stress can I put on top of that and still have infinite life? 0. None. Correct? Now, if you have stress is less than that, you can still put some alternating stress on top of that. But it can't be this much. So it's SE here, and it goes down to 0 in the example that I gave you. In the middle, your alternating stress will be somewhat smaller than this. So if I draw, remember that this is mean stress and this is all others. If I draw mean stress versus mean stress, this is what I get. That's like drawing x equals y. You get a 45-degree line. So if mean stress is 0, I can have that much SE. Let's increase that a little bit. That's okay. If the mean stress is now a little bit more, let's say over here, then this has to be reduced in order to preserve infinite life. So I can go up to maybe no more than that, a little bit more so I can get a good line. And then down here as well. Notice that this is smaller than that. So this point, what's the stress at that point? Remember, this is the alternating value of the stress. I'll write it here, sigma A. What is this? What does this stress indicate? The maximum stress, right? Sigma m plus sigma a. This value is sigma m. And of course, this is also minimum. I go up, I increase sigma a or sigma m a little bit more. Let's say over here, this has to be smaller, and a little bit over there, smaller yet, and so on. The same thing is true down in here. If I now draw a line through all of these points and draw a line through all of those points there, I went a little bit further than those, but you get points all over the place. This therefore shows you the maximum stress, and that shows you the minimum stress, right? The minimum stress is sigma a minus sigma m. If my stresses fall within this region, there is infinite life. If the stresses fall outside of that region, there's no infinite life. We do say that the material fails, but by failure we don't mean that as soon as you give it one cycle, it's going to break. It just means that it won't have infinite life. It will have a finite life. So that's what we mean. Even if we say it fails to have infinite life. Now, what's the limiting value of sigma max if the material is ductile? What can be its maximum value after which we shouldn't even be talking about fatigue? What if I increase the mean stress and I have a corresponding alternating stress, of course, until sigma max reaches the yield strength of the material in a ductile material? Then as soon as I load it, it will yield. So there is no question of fatigue anymore. The material is yielded. There's failure, static failure. Therefore, the sigma max must be limited to the yield strength of the material. So let's say this is the yield strength. It says we can't go beyond that point. And then we can go now to the other graph. If I continue that to the mean stress line, just like you see over there, like that, on the minimum side, that's as far as I can go. Agreed? If my mean stress is here and this is my alternating, the maximum is equal to Sy. Therefore, this graph must be limited to this region. So now, if you have the variation of your stresses from some maximum to some minimum, you calculate the mean and alternating values, you plot them here. You plot the mean on the abscissa and alternating on the ordinate. If your point falls within this region, it means there is infinite life with some sort of a factor of safety. We'll see how to find that factor of safety. If your point falls outside of this region, well, here it doesn't count, actually, it's over there. Then it means that the material will not have infinite life. There's fatigue failure. Any questions? Now, that's good for 10 to the 6. What if I don't want 10 to the 6? I want 10 to the 5. Then how would I change this diagram to make this applicable for a life of 10 to the 5? So that I can say, if my points plot here within this region, there will be a life of at least 10 to the 5. And if they plot outside of that region, won't have a life of 10 to the 5. What should I be changing here? SE to SF, that's right. SE to SF for 10 to the 5 cycles. In other words, rather than 10 to the 6 and SE, oh, these both can't be 10 to the 6, that's 10 to the 3. I come up here and say that's 10 to the 5. There's SF. Incorporate that over there. That'll give you, obviously, a larger safe region, right? Which makes sense, because you only want it for 10 to the 5, not 10 to the 6. But doing that every time for a new number of cycles is cumbersome. And therefore, we do it a little bit differently. This way. Well, I'll still keep this here so we can refer to it. Again, on the abscissa, we plot the mean stress. On the ordinate, we plot the alternating stress. If the mean, and again, for the time being, let's take a look at 10 to the 6, then we'll draw, draw a diagram for 10 to the 5 and all of that as well. Again, if I have completely reversed load, and notice the difference between these two. This one is just sigma A, not any other stress, number one. Number two, we won't even go into the negative part. We'll just treat sigma A as a positive value. But it is understood that it's like this. So, if sigma m is 0, no mean stress, completely reversed, then I can load this up to SE, right? And still have infinite life. Once again, this part is exactly the same as that. No change. Points fall over here, we have infinite life. Points fall there, no infinite life. And then we said, as we increase the mean stress, this alternating value decreases. We run tests, a large number of tests. We see that that's true. Test points that actually show failure look like this. And they are as badly scattered as I'm showing them. This is not very clean. Therefore, there's a continuous decrease of the value, or there must be a continuous decrease of the value of the alternating stress with an increase in the value of the mean stress, if we would like to have an infinite number of cycles. Is that okay? Or should I repeat that one more time? One more time. Looking at this graph with the experimental points, looking at this graph with what we just talked about, the increase of sigma m will lead to the decrease of sigma a. So here is sigma a, there is sigma m. Increase of sigma m leads to decrease of sigma a. You must decrease sigma a to still have a life of 10 to the 6. If you don't, there won't be a life of 10 to the 6. That's all that means. So we draw a line, but by the way, what's the limiting value here for sigma m? No sigma a, just sigma m. What defines failure then? Sorry? SY or SUT, depending on your failure criterion, right? If the material is ductile, yield strength. If the material is brittle, tensile strength. Since fatigue is a brittle phenomenon, we initially do use tensile strength. But this doesn't mean that this only is applicable to brittle materials. We will check for yielding as well. So initially, we will, however, use SUT. And we will draw this line. Now, this line starts with SE. That's the endurance limit of your part. Therefore, this line, since that is SE, this line indicates the limit of loading for infinite life. If your point, sigma A and sigma M, plot here within this triangle, we say the part will have infinite life with some sort of a factor of safety. If it plots out of this region, such as these failure points that you see, of course it will have failed. By failing, once again, we mean that there is no infinite life. This line is called the Goodman failure line. If you would like to take a look at failure region, taking into account yielding as well as fracture, then you draw the line between SE and SY. The difference is this triangle here. So this is obviously a more conservative failure criterion. So this is called Soderberg line. In reality, a much better fit to those points, to those experimental points, are not straight lines, but curved lines, such as a parabola or an ellipse. And I'll show you that on a screen as well. Any questions? So, these two lines define infinite life, one taking yielding into consideration, the other one not. Also, we find that when the mean stress is negative, this is mean stress positive. In other words, if we make mean stress negative and test here, we see that points fall like this. Shows no apparent decrease. Scattered, yes, but it shows no apparent decrease of the alternating value of the stress with an increase of mean stress in value, although it's negative. This sort of makes sense because fatigue is a tensile phenomenon. Compressive stresses don't propagate cracks. Tensile stresses do. Therefore, that makes sense, and of course, experiments bear that out as well. So your line here would be something like that. That defines failure under fluctuating load. By failure, I mean not having a life of 10 to the 6. Then I'll show you how to use these with the load lines and all of that in just a minute. We also said, any questions before I continue? Okay. We also said that if we want to draw this, not for a life of 10 to the 6, but for a life of 10 to the 5, 10 to the 4, whatever, that instead of SE, we will use SF, for example, at 10 to the 5, right? And then I'm not going to connect it. Well, maybe I'll connect it with a colored line. Those become your failure lines, correct? And you can have SF for any number of cycles you like. The easiest way to draw these might as well show you some of these as two. This is in your handout. The graph that you see on the very top is this graph. Is the one that I drew on the board. And notice that as you increase the magnitude of the mean stress, tensile mean stress, the magnitude of the alternating stress decreases. Large here, smaller there, smaller there, smaller there. So that's the same graph. Now, to construct the Goodman diagram, for example, from an SN diagram, this is from an example. There's your SN diagram on top. You go in here, you pick off the value of SE, that is SE because that's for 10 to the 6. By the way, as you look at these C's are modifying factors. This is from a different book. In that book, they call them C's, not K's. But they're the same. Surface size, whatnot. So, SE, you come down, plot over here, connect to SUT, and you get the Goodman line. You want it for 10 to the 5? That's for 10 to the 5. Plot here, come down, you get it for 10 to the 5. And so on and so forth. In fact, I see an error here. That should not be 80, that should be 75, right? On that line, we can't have both 80 and 75. But that's 75, comes from up there. Then for life of 10 to the 4, 92, somewhere in here, that's correct. And the 112 is just for 1,000 cycles, which you can take it or leave it. You can do a static analysis if you wished. That's low cycle fatigue. Okay? Notice that so far, everything that I've said depends on the material. These are all material properties. I haven't said anything about loading yet. All I said is we can load this to a property of the material. A property of the material. A property of the material. The property of the material is similar to the yield strength or the tensile strength. They're very good, and as soon as you have a material, you have all of those, as you have all of these. But then you also have an applied loading. So how do you combine these two to give you a meaningful way of analyzing fatigue problems? Here's what we do there. We draw what is called a load line. And to do that, I'll draw that over here. Probably will go over a little bit, but I'll give you a break. A little bit late, but I will give you the break. So we said, let's draw our strength lines. These are our strength lines. What I'm about to do is exactly what we did when we applied failure theories in static loading. For example, in maximum shear stress, this is what we did. We said, here is the failure locus. There is my load line. Remember that? Strength line, load line. You draw the load line, you draw the strength line. Whenever they cross, that's your limiting value. And you use that to find factors of safety or say whether the part has failed or whatever. We're going to do exactly the same thing except with this failure criterion. And all of this is 410 to the 6. But the only difference would be that you draw fresh lines if it is anything other than 10 to the 6. But the basis remains the same. So here is SE. There's SUT. And I'm just going to use the Goodman line and not the Soderberg line. We'll correct for yielding in just a second. And what if I have a case in which the material is ductile and the mean stress is equal to the yield strength of the material? The material is ductile. The mean stress is equal to the yield strength of the material. How much alternating stress can I put on it? None, right? We already yielded the material, so we're over here. So alternating 0, yield, so this is SY. I'm not going to draw the Soderberg line, but a different one. What if the mean stress is 0? The mean stress is 0. And sigma A, in other words, the alternating stress, happens to be equal to the yield strength of the material. How many cycles? A half, actually a quarter, right? As soon as you load it, you load it to yield strength, right? So the material yields, it's ductile. So this could be 0, and that could be over here somewhere. Is that about the same size? Yeah. This is called the yield line or Langer line. This shows you the limit of values of sigma A and sigma M that you can put on the material and have no yielding. So this is another failure theory. Anything inside here is safe. Outside will have yielded. The equation of that line is maximum stress is equal to SY. That's the equation of that line. And of course you can check it. Put this one 0, that one is equal to SY. Put that one 0, sigma A equals SY. So there's your line. So if I am not willing to have the material yield, and I also want a life of 10 to the 6 for the part, 10 to the 6 cycles of stress, I'm limited both by this line and that line. In other words, I'm limited to this region. Agreed? If my point plots here within this region, the material will not yield and it will have a life of 10 to the 6. If it's outside, not so. I'll show you about the factors of safety and all in just a second. The same thing on this side. With sigma M negative, of course there it's just a straight line like that. So we can pick off SY on this side too. Remember that yielding has nothing to do with tension and compression. It's a shear phenomenon. And therefore, whether you're applying a tensile stress or a compressive stress, doesn't matter. The material yields just as easily with SY. So this is the Langer line for here. There's the Goodman line in the negative sigma M part, and then we have this safe region within this red failure line, unsafe region, meaning either yielding or lack of infinite life outside of that. Any questions on those before I go to loading? Those are all still properties of the material, nothing else. If I have unapplied load, I calculate sigma A and sigma M, and I will plot my point. Let's say it plots here. My load line goes from the origin through that point and continues. If I continue increasing sigma A and sigma M by the same factor, 2 times, 3 times, 5 times, whatever, the failure would be of what kind? What kind of failure will occur for that load line that I just drew? Sorry? In other words, yielding. That is correct. A ductile failure will occur. This is the yield line. That means if your point falls on that line, the material is about to yield. And I'm saying I multiply this until it crosses that line. And it crosses this line before it crosses that line. So failure here is by yielding. Your factor of safety is Sy over sigma max. Any questions? You guys have a question? No? Sure? Okay. Everybody okay with this? The factor of safety is, actually maybe I should write it that way. N equals OB over OA equals Sy over sigma max. It is also equal to we call the limiting value of the mean stress, we call Sm. The limiting value of the alternating stress, we call Sa. So as you can see, this N is also equal to Sm over sigma M, also equal to Sa over sigma A. Any one of those will give you the factor of safety. They're all the same. Any questions? Okay. Point plots here. I'll call this sigma A1, sigma M1. There's my load line. Those are my strength line. Failure is by fatigue. Lack of infinite life. Remember, this is the Goodman line. Your point plots here, we have safety. Plots out, we have lack of infinite life. So if I increase these values until these two cross, then that's what I have. So in that case, let me write that in black so you can decipher it. N equals OB prime over OA prime is equal to, call this SM1, call that SA1, equals SM1 over sigma M equals SA1 over sigma A. Any questions? Point plots. This is getting crowded. Point plots here. So here's my load line, this time in red. What's the factor of safety here? My point has plotted here. So I have a sigma A2 and a sigma M2. What's the factor of safety? I'm sorry? You mean SM2, but I don't have an SM2. Notice this is just straight like that, right? Factor of safety is that distance divided by that distance. Agreed? Is that not the same as this distance divided by that distance? So factor of safety is equal to SE over sigma A. Agreed? If there's any part of this you don't understand, please let me know now, because we're going to be using this. And finally, if your point plots out here, once again you cross the yield line before you cross the fatigue line, and the factor of safety is Sy over sigma max. In this case, absolute value. These are the 4 different types of failures that you may encounter. And those are the factors of safety that you get for each. This is a bit crowded, I guess. But if you're going to put it all in one graph, this is what happens. So what we do is this. Draw our strength line, draw our load line, write an equation for that, write an equation for that, solve the 2 equations together, find the coordinates of this point. Then the factor of safety is that divided by that, or that divided by that, or OB divided by OA, however you want to calculate it. They're all the same, exactly like what we had in previous failure theories. No change. There's a strength line, there's a load line, you find the cross section, and that gives you your limiting values. All right? Okay, let's take a break. Unless there's a question. Okay, let's take a break. One thing I need to correct here. At sigma A, I wrote it as sigma A, but it should be sigma A2, this value. It's that divided by this. So that's sigma A2. Okay. In your book, you also see this picture here. And that's the same thing as I drew over here, with all of the experimental points, and you see where the experimental points fall. And this is SM over SUT, so that's SUT basically. And this is SA over SE prime. Now SE prime is the endurance limit of the rotating beam, but you can use this diagram for either SE prime or SE. You just use the corrected value of SE prime if you want to use it for SE, that's all. Any questions? What we talked about insofar as factors of safety are concerned and how you find them, they're tabulated. Oh, actually before that, let me talk about this. As I mentioned before, the failure points here are much better represented if we do not use straight lines, but curved lines. And notice that the straight lines are more conservative than the curved lines. In other words, they limit your values to these triangles here, whereas the curved lines got a little bit more room in here where you can load the part and still essentially have infinite life. This is all for infinite life. 2 lines are drawn here. One from SE to SUT called the Gerber line. It's a parabola. And one from SE to SY, which is called ASME elliptic, and as the name implies, it's an ellipse. This second one, ASME elliptic, is used extensively in industry. And that is the main type of failure locus that they use. We will use those as well. If you're asked to use these, you can use the equations that I'll be going over very briefly right now. But I will show you an example in which I actually write the equation of the Soderberg line, or not the Soderberg, the Goodman line, and not use the equations on the book. So if the failure locus is linear, you should be able to write the equation of the load line, write the equation of the failure line, just like you did for static failure, solve them together to find the limiting values, and then the factor of safety. By limiting values, I mean these: SM, SM1, SA1, so on. But if your failure criterion is one of nonlinear kind, then you can go ahead and use the equations in the book to find the factor of safety. But still, you must understand what they mean. So these are tabulated in 3 tables like this. The intersecting equations, those are the 2 equations of the load line and the strength line. And notice that these equations you can write very easily. Of course, the load line is just sigma A equals M sigma M. Load line and at limit, and that's where we look at it. Meaning when it crosses the strength line, then it becomes SA and SM. This is the one we use, SA and SM. In other words, we want to find the coordinates of points such as this. The equation of the Goodman line is a straight line equation, very similar to the maximum shear stress. So you can write it like this: SA over SE plus SM over SUT equals 1. This is the Goodman line. You can test that. If SA or sigma A is 0, SM equals SUT. If SM or sigma M is equal to 0, SA equals SE. 2 points on that straight line, that's the equation of that straight line. I'll demonstrate this in an example problem that I'll do on the board. Well, actually, no. It's on the screen, and you do have its solution. The other failure criteria, this is for modified Goodman and Langer. Then you have one for ASME, Gerber, and all of those. So, and look at, there's your factor of safety right there. And as I said, for nonlinear cases, you can go ahead and use that. But you do need to have an understanding of where it comes from. In other words, if I take the equations away from you, you should be able to do it graphically. That's what I mean. That's when you know this stuff. Don't worry, I will not make you do that. But that's the way, that's how you should learn the material. In other words, if there are no equations, what do you do? Can't commit suicide. That's too harsh. Any questions? Okay, let's take a look at this example problem. This example problem is from your book with a little bit of change. The change essentially comes from the fact that, unfortunately, these publishing companies make meaningless changes to the book to come up with a new edition and make more money. And it's a shame that they do that, but they do that. And this example 629, this is a problem in your book, is a case in point. If you take a look at example 629, which used to have different dimensions. It's a little bit different than what we have here. So these are the changes. So please write these on your paper. I have written them, but you should write them as well. As you see, I say on the very top, example 629 with the following changes of dimensions. L is equal to 100, not 140 millimeters, and the cross section is 18 by 3, not 20 by 4, I guess. Let me draw the picture here, and then we'll read the statement of the problem. It says, the figure is a drawing of a 4 by 20 millimeters. So in our case, this is 3 by 18. And this length is 100 millimeters. Latching spring, 4 by 20 latching spring. A preload is obtained during assembly by shimmying under the bolts to obtain an estimated initial deflection of 2 millimeters. So before any latching operation occurs, you shimmy under the bolts here, and this is held against something, so that the deflection would be 2 millimeters, and therefore a load will have to be applied to give it that deflection. The latching operation itself requires an additional deflection of exactly 4 millimeters. So that's when the latching operation takes place. The material is ground high carbon steel, bent, then hardened and tempered to a minimum hardness of 490 Brinell. The inner radius of the bend is 4 millimeters. So that's the radius here. And they only give you that because they would expect you to use curved beam equations to find the stresses. In our case, we haven't done curved beam. So we're not going to use curved beam equations. We'll just apply a stress concentration factor to take care of that. Okay? I'll emphasize that. Estimate the yield strength to be 90% of the ultimate strength. So you have the Brinell hardness, you can find the ultimate strength, and then the yield strength. Find the maximum and minimum latching forces. Determine the fatigue factor of safety for infinite life using the modified Goodman criteria. Modified Goodman is this red line here. This is the Goodman diagram, and it's been modified by these two yield lines, the Langer lines. So that's why it's called the modified Goodman diagram. All right? So, yes, too big, I guess. SUT equals 3.41 times 490. This is the relationship between the tensile strength and hardness in the metric system. It's the same as 0.5 HB in the English system. So 1671 MPa is the tensile strength of the material. I've used this equation, although it goes a little bit past 495, which is the maximum that you have for the Brinell hardness. But let's use that anyway, 1671. Moment of inertia of the cross-section. This is your cross-section. You find its moment of inertia, 112 bh cubed, 40.5. And then it says to find the minimum and maximum load. The minimum load is what comes from shimmying under the bolts. In other words, what gives this cantilever beam a deflection of 2 millimeters initially. So deflection of 2 millimeters here on a cantilever beam. For a cantilever beam, deflection is equal to FL cubed over 3EI. Therefore, the force is 3EIY divided by L cubed. So this is a modulus of elasticity for steel. I, Y, the 2 millimeters, and L cubed, 100 cubed. 50.3 newtons. F max is 3 times F min, because Y max, the deflection, maximum deflection, is 3 times the minimum deflection. So it says the shimmying gives it an initial deflection of 2 millimeters. The latching operation involves 4 millimeters of deflection in addition to that. So that's a total of 6 millimeters. Therefore, the maximum is due to 6 millimeters of deflection. The minimum is due to 2 millimeters of deflection. Therefore, the maximum force is 3 times the minimum force. So there's the maximum and minimum forces. Using those, we find the alternating and mean forces. You don't have to go to stresses to do this. You can do it with forces or moments. And this is what I was talking about when I said we use a stress concentration factor for the curvature. We use a stress concentration factor of 1.5 for the curvature. And this is due to curvature verified by curved beam equations. And we find the mean and alternating stress. And this is only bending. There is no other load. So the alternating value is KAMC over I, where K in this case is the stress concentration factor. You might want to just point that K to that 1.5. The stress concentration factor, by the way, should be applied to both the mean and the alternating value of the stress. So we find the stress concentration factor, in this case given. We assume it to be the same for fatigue and geometric, and we don't make any corrections here. Or maybe no, when I use it for fatigue, I think I'll make a correction. This is only for static loading. So K times M, which is 50 times 50.3 times 100. Minimum value of this load is 50.3. Alternating value, sorry, which is the same as the minimum value. Times 100 times C, 1.5, half of 3. That's where that comes from, divided by I, 279. The mean load is twice that, because the mean force is twice the alternating force. So the mean stress is twice the alternating stress. SUT 1671, estimate SY as 0.9 SUT, and find the factor of safety due to yielding. Because if this material does not have a yield factor of safety, there's no sense in doing a fatigue analysis. It will have yielded under the static stresses. So factor of safety is y over sigma max. Notice that that's this one. So if you were to draw your load lines and strength lines, this would be the factor of safety. Now, it may be governing this, maybe not. In other words, it's either here or over there, one of those two. But this is the cross section. And that's the way you check for it. You don't have to do it graphically all the time. So we're OK with yield, factor of safety of 1.8. SE prime is 700 MPa because we found that SUT is larger than 1400, so it remains at 700. Remember, there was a limit to that. SE prime equals 0.5 SUT. The limit was with SUT equal to 100 KSI or 1400 MPa. Sorry, 200 KSI or 1400 MPa. So that's where that comes from. That's equation 6.8. Surface factor, this is what we discussed before, 0.841. In the size factor, you come here and you take a look at the cross section, and of course it's not round, and this is not rotating, bending either, so you must come up with an equivalent diameter. The one what we talked about last time. So the equivalent diameter is 0.808 hb to the 1/2. This is the equation we put on the board. I put on the board last time for rectangular cross sections. 5.94. In other words, this is equivalent to a member with a diameter of 5.94 millimeters if it were rotating bending. That's the meaning of the equivalent diameter. KB, therefore, is 5.94 divided by 7.62 to the minus 1/7. Notice that KB is larger than 1. This will always be the case if the diameter of the part that you're looking at is smaller than that of the rotating beam specimen. The rotating beam is 7.62. That's why you divide this by 7.62 right there. So that's a little bit larger than 1. Therefore, SE is equal to the modifying factors, only 2 in here. The rest of them we assume 1, unless it says otherwise we assume 1, times 700, 605 MPa. Notch sensitivity is 0.95. We have to convert the geometric stress concentration factor that we have assumed, 1.5, to a fatigue stress concentration factor. So Kf is equal to Q times Kt minus 1 plus 1, 1.48, slightly less than the geometric stress concentration factor. So the stress concentration factor times sigma A will give you this. And notice that I'm dividing 279 by 1.5, multiplying by 1.48. Let me show you why. In the static analysis, I used this stress concentration factor right there. You see that? That's the stress concentration factor, K. And I got 279. Now my stress concentration factor is no longer 1.5. It's 1.48. So either I multiply sigma A by 1.48, or what I've done here Either I do that, or I divide the 2.79 by 1.5. That takes out the stress concentration factor that I used, and then multiply it by 1.48. So all I want to do is multiply 1.48 by the value of sigma A. Kf sigma m, 2 times that, because the load is 2 times that, so 550. Load line is, this is the slope of the load line, or you can say SA over SM equals 0.5. Here is a subtle point that we write the equations, this equation, for the point of cross section of the two lines. This is the Goodman line, and here's the load line. I write the equation of both lines with the coordinates of that point. My point, which we will plot here, in fact, we have the stresses, 367, 183.5. That may fall here. This is sigma A, and that's sigma M. Kf sigma M, Kf sigma M. But I write the equations for this line with these coordinates. The reason being that I want to solve this line, the equation of that line, the equation of this line, both written for Sm and Sa, not sigma A and sigma M, so that when I find the coordinates of the cross section, it will be the values of Sa and Sm. So I'll write the equation of this load line like this. Sa equals Kf sigma A divided by Kf sigma M times Sm. This is the slope of the line, that divided by that. That's Sm, or sigma M, but Sm because we're writing it for this point. This is Sm. That's Sa. I will also write the equation of the Goodman line for exactly the same point. So I say Sa over Se plus Sm over Sut equals 1. Now if I solve these two equations together, I find values for Sa and Sm, my limiting values. So don't write them in terms of these, just use that to find the slope of the load line. So that's what I've done here. Load line Sa over Sm is equal to 0.5. The reason is that Kf sigma A divided by Kf sigma M is 0.5. So Sm is 2 times Sa. There's the equation of the load line, right there. That's the equation of the Goodman line. This with values substituted. So I now substitute for Sm, 2Sa, and I solve for Sa. Factor of safety, therefore, then, is Sa divided by Kf sigma A, or 1.3. They're all shown here in this sketch. And you should draw a little sketch for yourself. To approximate scale, you don't need to be that accurate. But the more accurate you are, the more helpful that sketch will be. So draw a sketch for yourself and make sure that you understand the relationship between the graphical representation and the analytical representation. Any questions?
For the Sy equals 0.9 SUT, where did the 0.9 come from?
The book says assume the value of Sy to be 90% of SUT. Okay. If you read the statement of the problem, that's what it says. Okay? Anything else? Okay. There's, I think, 5 or 6 example problems in your book. on this stuff. So read them, make sure you understand them. It would be best for you to do them yourself first, then go read them. Don't read the solution. And for those failure criteria that use linear failure methods, such as the Goodman or the Soderberg, use this method. Write the equation of the two lines and solve them together. Because somewhere along the line, in a quiz, exam, or a final, I'm going to ask you to do exactly that and not use the equations in the book, but only for linear failure criteria. I will not ask you to do that for the Gerber or the ASME elliptic, only for linear criteria. Soderberg and Goodman, you must be able to do that. Any questions? Okay? Now, here, as you can see, we only had one type of loading. This loading, in this case, was bending. It could also be torsion. If you have pure torsion, then you can use the same method. You can use the Goodman line and the load line exactly the same way. With one change, well, actually two changes. We see that if the torsional mean stress, what we would be plotting on this axis if this were torsion, the torsional mean stress has no effect on the endurance limit of the material, provided the material is ductile, polished, and notch-free. In other words, no stress concentration. Otherwise, the same story happens there as well as here. So if you have those cases, in other words, polished and all of that, then you don't need to do anything. You don't even need to consider SM, provided the value of sigma m, the mean stress, is less than the yield strength of the material. In other words, you're not yielding it right away. Otherwise, draw Goodman line, load line, exactly the same with these substitutions. Ultimate strength in shear, SSU, we take that approximately as 67% of SUT. SSY, we've talked about this before, comes from the von Mises consideration. It's 0.577 SY. This is yield strength in shear. And of course, you must use Kc equal to 0.59, which theoretically is actually 0.577. This is for pure torsion, not combined with anything else. But the discussion remains exactly the same. Any questions? Now, in almost all cases, we don't have just one type of loading. We don't have just bending or just torsion or just axial load. We're combined. That's why we did von Mises, for example. This is no different either. And what we are about to talk about is the analysis of fatigue in combined loading, provided that the loads go up and down in phase. Wherever the bending load is maximum, the torsional load is maximum at that time, the axial load is maximum at that time. Whenever they are minimum, they're all minimum together. and they go up and down in exactly the same manner. This, for example, an example of it would be this type of loading. I don't have to write anything on it. This is self-explanatory. Take a look at this. This is under bending and torsion, right? Whenever the bending stress is maximum, the torsion is maximum at that time too. Whenever it's zero, torsion is zero too. Because that means that this load is not there. The load is there, they're all there. And they vary with that load. This is called varying in phase. Should they vary out of phase, then you have to bring in what is called a phase angle. You remember that from your physics courses, sine of omega t plus phi and all of that, the difference in the phase angle. When you have something like this, one of them varies like that, the other one maybe varies like this. The maxima and minima don't necessarily occur at the same time. We're not going to deal with that. But this is just for your information, that if you have them out of phase, then you have to bring in the phase angle. To treat problems of combined loading, we make use of the von Mises theory. Because remember, all that von Mises does is turn a combined loading case where you have all sorts of stresses into one. So we take normal stresses, shear stresses, axial, maybe bending, whatever, and we combine them all into that sigma prime. We do exactly the same thing here, except we do it twice. We do it once for the mean stress, once for the alternating stress. Okay? The procedure is this. I will write it on the board. One, for strength, use the fully corrected endurance limit for bending. In other words, regardless of the type of loads that you have, calculate that as though this was pure bending. No torsion, no axial load or anything like that. We take care of that in subsequent steps. 2, apply fatigue, stress, concentration factors to I should say apply respective fatigue, stress, concentration factors to sigma m and sigma a, just like what I did on the board in that example problem. But what I said was respective, meaning that, not sigma m and sigma a. Sigma bending, sigma axial, and sigma torsional, not sigma a and sigma m. apply fatigue stress concentration factors to these. Respective means this has one stress concentration factor, that has a different stress concentration factor, that has a different stress concentration factor. Same discontinuity. I'll demonstrate this in an example problem next time. Multiply any alternating component of axial load by 1 over 0.85, which is equal to 1.173. This is the load factor for axial load. We talked about that last week. That's the load factor. Remember the load factor? 1 for bending, 0.85 for axial load, 0.59 for pure torsion, what I just had, Kc. So rather than decreasing the strength, in other words, multiplying this by SC prime, we're increasing the stress by multiplying by this, but only the alternating component. 4. Use Moore's circle to find principal stresses, maximum and minimum. 5, use results of 4 to calculate mean and alternating values of von Mises stress, called sigma m prime and sigma a prime. Six, compare sigma a prime and SE. Do call it SE here, I guess. For completely reversed loads. Or use Goodman diagram for fluctuating. For fluctuating loads. You can combine steps 4 and 5 and not find principal stresses. So long as you can find the von Mises mean and alternating stress, that's okay. That's all you need. And remember, you don't always have to have principal stresses to find von Mises. You may use that equation that is for one normal stress and one shear stress. Remember this equation? Sigma equals sigma prime equals the square root of sigma squared plus 3 tau squared. You don't find von Mises. You don't find principal stresses. You just find von Mises. So you can combine steps 4 and 5. You don't always have to find the principal stresses. If it is complicated, it's best to find the principal stresses. If not, you can use it that way. This is essentially exactly the same type of an analysis that we just did with the example problem that I had, except at first you had to use whatever you learned from von Mises to convert a complicated state of stress into just two stresses, sigma A prime and sigma M prime. And then you draw your Goodman diagram, and just like sigma A and sigma M that we've plotted here, you plot sigma M prime and sigma A prime. Because you've converted that as though there was only one stress, not a combination thereof. Okay? I will illustrate this in an example problem next time. So I have a few minutes. Next time when I go over, you shouldn't complain. I'll see you on Thursday.